Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory undergraduate combinatorics based on my book, An Invitation to Combinatorics. The subject of this lecture is non-attacking rooks and forbidden positions. So consider the following 6x6 board. This is a board that has 6 rows and 6 columns, and some of the squares are forbidden. They're crossed out. You can't use them. And what I want to do is I want to place 6 non-attacking rooks on the non-forbidden positions, outside of the forbidden positions. And I want to know in how many ways this can be done. So I want to put 6 rooks here, but not in these crossed out squares. And I want them to not be able to attack each other. And I want to know how many ways can that be done. First of all, rook, which comes from the Persian roch, is a chess piece. In many languages, like German, it's called some version of tower. In German is Turm. In Finnish is tourney, and in Spanish is torre, and so forth. It's a chess piece, and the way it moves is that it can go horizontally and vertically. If you want two rooks not to attack each other, then they can't be in the same row or column. So all we're asking for is picking squares on this 6x6 board so that no two of them are in the same row or the same column. And I want to know how many ways I can do that. I might put one rook in the first row. I can put it in the fourth column. Here's another one. Here could be one way that I can put 6 rooks on this board with none of them attacking each other because no two of them are in the same row or the same column. And the question is that how many different ways I can do that. I'm going to first do 2 cases where you know how to do it, or at least it's easier. Let's say that I just had a 6x6 board and no forbidden positions. I could put the rooks anywhere I like. To put 6 non-attacking rooks, first of all, I have to put 1 in each row. For each row, I have to decide which column it goes in. So all I have to do is tell you what the column numbers are. Whatever column numbers I put for the first row, for the second row, and so on, and those column numbers cannot be the same. Therefore, I get a permutation of 1 through 6. So placing 6 rooks on this board in a way that they do not attack is in one-to-one correspondence with all permutations of 1 through 6. So for example, 4, 3, 1, 2, 6, 5 is a permutation of 1 through 6. That corresponds to a rook placement. That 4 at first says, in the first row, put your rook in column 4. Then you get a 3. So that means in the second row, put your rook in the third column. And then you get a 1. So you put it in the first column. And so these are column numbers. A permutation, the order matters. So you know the first one is for the first row, the second one is for the second row. It's telling you where the columns are. And so if you continue, this is what you get for that particular permutation. If you give me a different permutation, it'll give me a different rook placement. And if I give you a rook placement, that will automatically give you a permutation. There's a one-to-one correspondence with all permutations 1 through 6 and all rook placements on a 6x6 board. And because of that, the number of ways of placing n non-attacking rooks on an n by n board is the same as the total number of permutations of 1 through n, and that's n factorial, as long as there's no forbidden permutation. The n factorial, the argument is very simple. How many choices do you have for the first row? You have n choices. For the next row, you can't use that one, so you have n minus 1 choices, then n minus 2 choices, and so forth. You have n factorial choices altogether. So if there's no forbidden positions, then the answer is n factorial. So here's another example. Another example is when the forbidden positions are the main diagonal. The main diagonal is forbidden. Everything is open. If forbid the diagonal entries, then that means you can't put the ith rook, the rook in row I, can't be in the ith column. And that what gives you is a derangement of 1 through n. A derangement is a permutation where 1 through n, none of them are in natural position. Not in its natural position. So 1 is not in the first position, 2 is not in the second position, 3 is not in the third position, and so forth. And that corresponds exactly to a placement of rooks where you're not allowing 1 in its first position, 2 in the second position, and so forth. 4, 3, 1, 2, 6, 5 is like that because I didn't put anything on the diagonal. And if you look at the permutation, none of the integers 1 through 6 are in their natural position. Like 6 would like to be in the 6th position, but it's not. It is in the 5th position. And 2 is not in the 2nd position, it's in the 4th position, and so forth. And we know how to count those. Another video on derangements went through this in some detail and gave us an answer to how many derangements there are. So number of ways of placing non-attacking rooks on an n by n board with all main diagonal entries forbidden, and those are the only ones that are forbidden, then is the number of derangements. And again, in a different video, we showed that that's given by n factorial times a partial sum, and actually that's the partial sum of the series expansion for 1 over E. I'm not going to prove that here. I did prove that in another video using inclusion-exclusion. Okay, now I want to go to the general situation. So a general situation is that you've got some board and some of the not necessarily the main diagonal, but some of the entries or some of the squares are forbidden, and you can't put a rook there. And so the question is that how many ways can you put 6 rooks there? Of course, if you forbid too many things, the answer will be 0. You can't put them. But for example, here you can, as we have seen, you can put 6 rooks there that not attack each other. And the question is that how many ways can you do that? So for such a general arbitrary thing, there's not going to be a general formula because very much depends on which squares are forbidden. However, we can use inclusion-exclusion principle to change the problem around. That's what inclusion-exclusion usually does. It changes on it, it turns the problem on its head. And so using inclusion-exclusion, we can translate problem into one of placing non-attacking rooks in the forbidden position, as opposed to using the answer to how many ways can I put rooks in the forbidden positions. I can get the answer to how many ways I can get how many ways I can place non-attacking rooks not in the forbidden positions. And that's sort of interesting that we can do that. This is going to be useful if the forbidden positions are structured in some way or they're sparse, there are not that many of them. Then switching to putting the non-attacking rooks in the forbidden positions makes sense. Otherwise, it would not make sense to use this system. And so let me remind you of inclusion-exclusion. I have another video on inclusion-exclusion where I go through the proof of the inclusion-exclusion principle in some detail. I'm not going to do that here. I'm just going to tell you what it is. If you have a set and if you have a bunch of subsets, and if you're looking for, and these subsets might be overlapping in various which ways, and you want to find out the number of elements in the set that are in none of the subsets. So A1, the size of A1 complement, the complement of A1 in S, the intersection of A1 complement with A2 complement, with A3 complement, all the way with AM complement. You want to know the size of that. So A1 through AM are the subsets in your set of the types of elements you don't want, and so you want to know how many things you do want, which are in none of those subsets, and that's what you want to find. And the inclusion-exclusion principle says start with the ambient set, the size of set S, and then throw out the stuff you didn't want. You didn't want the elements in A1, so throw out the size of A1, throw out the size of A2, and so on. But you've overdone it. You have to put back pairs of intersections, because every pair of intersection got like A1 intersection A2, anything that was in them got thrown out twice. So you have to add in the size of the pairs of the intersections of two of the sets back in, but you have overdone that again. You have to take away the sizes of all triple intersections, and so on and so forth, all the way till the end. And so there's a lot of terms here. For example, how many triple intersections there are? There's one for each subset of size 3 of a set with n elements, and there's one for each subset of, there's a term here for each subset of size 2 of a set with n elements, and so forth. So this is the inclusion-exclusion principle. If you're not familiar with it, watch my video on inclusion-exclusion. So we want to now apply the inclusion-exclusion principle to our rooks on the board with a forbidden position. So let's have a setup for that. For inclusion-exclusion to work, you want to always make sure that your setup is correct, that you have a ambient set, you know what the sets A are, what are you counting, and to have some idea that you can actually do the count. So we have an n by n board with forbidden positions, and here's our setup. So Sn is going to be the set of all permutations of 1 through n, and that corresponds to all rook placements, n rook placement, placing n rooks on this n by n board with no forbidden positions. And we know how to count those, it's just n factorial. But then there's some of those that we don't want. AI is going to be those rook placements where the ith row rook is in the forbidden position. So because we're placing n rooks, every row is getting 1 rook, and that rook might be causing trouble or not. It might be in a forbidden position or not. AI is those, we don't care what happens in other rows, but for row I is the ones where that ith rook, the rook on row I, is in a bad place and is in a forbidden position. And so We don't want things that are in A1. We don't want things that are in A2, all the way to things that are in AN. And therefore, what we want are the number of elements, the number of permutations that are not in A1, but also not in A2, but also not in A3, all the way till AN. So we want A1, the size of A1 complement, intersection A2 complement, intersection AN complement. So this is our setup for inclusion-exclusion. So let's now apply it. So again, we have an n by n board with forbidden positions, and Sn is my set of all permutations. Again, that's with no restrictions, and AI is those where the ith row rook is in a forbidden position. And I'm going to introduce another notation. Rk is going to be the number of ways of placing k non-attacking rooks in the forbidden positions. So how many, if k is 1, how many ways can you place one rook in the forbidden positions? Non-attacking rooks? Well, that's just going to be the number of forbidden positions. R2 is going to be the number of ways to be placing 2 non-attacking rooks in the forbidden positions. The beauty of inclusion-exclusion is that it allows us to switch back and forth between forbidden positions and non-forbidden positions. We wanted to put things in non-forbidden positions, but inclusion-exclusion directs us to actually put things on the forbidden positions. So let's see. But to do the inclusion-exclusion, among other things, I have to find the sum of these bad sets, the sum of the sizes of AIs. Now, what is the sum of the size of AI? A1 is all those permutations where the rook and row 1 is in a forbidden position. A2 is where the rook and row 2 is in a forbidden position. If I add them, if you think about it a little bit, you get the number of ways of placing n non-attacking rooks on the board with one designated rook in a forbidden position. It might be the rook in the first row designated, or rook in row 10 designated. One of them is designated. That guy got to be in a forbidden position. The other ones can be anywhere they like. They could be in forbidden positions or not. That's what the sum of these is. And I can count that, the totality of that, in a slightly different way. I can say that, okay, well, if I want to sum that, first I decide which is the designated rook that's going to go in, the designated rook that's going to go in a forbidden position. I'm going to pick that. And the number of ways I can do that is R1, because that's the number of ways of putting one rook in a forbidden position. So put that. So that's going to be your I. That's going to be the guy, the row that's causing trouble. After that, you don't care. Everything else can go anywhere they like. And what you have then, you have n-1 choices for the first remaining row, because the only thing you can't use is the column for this rook that you already put down, the bad rook that you already put down, and then n-2 choices for the next one, and so forth. And so the total number of choices is R1 times n-1 factorial. That's going to be the sum of all the AIs. Okay, so you might want to think about that one more time. But what about the sum of the pairs of intersections? Well, that's going to be the number of ways of placing non-attacking rooks on the board with 2 designated rooks in forbidden position. Maybe I want the first rook, the rook in row 1 and row 3 to be in a forbidden position, or the rook in row 4 and row 5 in a forbidden position. But at the end of the day, I will have 2 rooks in forbidden positions, and then after that, I don't care. I could put them in forbidden positions or not, but I don't care. So I can count that in a different way also. I can say, well, first, put 2 rooks in a forbidden position. How many ways can you do that? Well, that's R2. That's exactly what the definition of R2 is. How many ways can you put 2 rooks in a forbidden position without them attacking each other? After you've done that, you've taken care of, was it A1 intersection A2, A3 intersection A4, whichever one it was, you needed 2 rooks. You've done all the possible ways of putting those 2 rooks, and after that, you don't really care. But 2 columns are now off board. You're not allowed to use 2 of the columns because you've put 2 rooks there. So for the next one, you have n-2 choices, then n-3, and so forth. And so it's R2 times n-2 factorial. And all of the other intersections is going to be the same. So here's the final result. If you have n by n board with forbidden positions, and then the theorem is going to say like that: the number of ways of placing n non-attacking identical rooks on an n by n board with forbidden position. I'm saying identical rooks because I don't want to get confused to say, oh, I have white rooks and black rooks. Can they attack each other? 2 white rooks can attack each other. Yes, they can. So all the non-attacking rooks are identical, and I'm putting them in an n by n board with forbidden position. And the answer is going to be equal to this thing that's given to us by the inclusion-exclusion. N factorial is the total number of permutations with no nothing, no worry about what's forbidden not. Then R1 times n minus 1 factorial, as we saw, is the sum of the size of AI. R2 n minus 2 factorial is the sum of the size of AI intersection AJ, and that continues all the way till the end. So this is what we get from the inclusion-exclusion. And what is RK? RK is the number of ways of placing K non-attacking rooks on the n by n board so that each of the the rooks is in a forbidden position. So this is our final result. But the proof of the pudding is in the eating. Let's see if we can actually use this in our example. Okay. So, and this takes a little bit of work, and inclusion-exclusion, as usual, is not the go-to place for when you start a combinatorial problem. But often, like this, in this case, you don't have better choices. So, so we've got to do it. So let's see. So we want to know a number of ways of placing 6 non-attacking rooks and avoiding these forbidden positions. So an RK, the key thing is the number of ways that you can place K non-attacking rooks in the forbidden positions. Now here in this particular example, the forbidden positions have a nice structure. They come in 2 groups, these groups on top and this group on the bottom. So I'm going to give them a name. F1 is going to be forbidden positions in row 1 and 2, those 3 squares in the corner up there. And F2 is going to be the forbidden positions row 3 and 4. And the key thing is that no rook in F1 can attack in rook in F2 and vice versa. So if I place things in there, I can also place things in here at will, and there's no problem in them attacking each other. Okay, so I have the same setup, the same board, and the same F1 and F2. And now I want to figure out what the R1, R2, those things are. So how many ways can I place 1 rook? That's what R1 is. How many ways can I put 1 rook on the forbidden positions? Well, that's just the same as how many forbidden positions there are, and that's 3 plus 4 is 7. But how many ways can I put 2 rooks in there? Well, I've got 2 choices. I could put both of them in F1, I could put both of them in F2, or 1 in each. If I put both of them in F1 up here, there's only 1 way to do that. If I put both of them in F2, there's 2 ways to do that. And if I put 1 in each, well, I can put 3 things here and 4 things here. 3 times 4, 12 ways. So the total number of ways of putting 2 rooks is going to be 1 for putting both of them in F1, 2 for putting both of them in F2, or 3 times 4. This is where it's helpful to know that F1 and F2 are separate from each other, and rooks on each on those cannot attack each other. So I can put any rook on that one and any rook in here and be happy with it. So that's 12, and so that's 15. What about 3 rooks? Well, I can put that 2 in F1 and 1 in F2, or vice versa, 2 in F2 and 1 in F1. If I want 2 in F1, there's just 1 way to do it, but then there's 4 ways to put 1 in F2, so that's 1 times 4. But if I want to put 1 in F1, there's 3 ways of doing that, and 2 ways of putting 2 in F2. That's 3 times 2, 6. That's 10 ways. What about 4 rooks? The only way to do that is to put 2 in F1 and 2 in F2, and there's only 1 way to do that in F1 and 2 ways to do that in F2. So R4 is going to be 2. So I've got all my ingredients to now use to finish my example. So again, the same board. We might be getting tired of this board. And RK is the number of ways of placing K non-attacking rooks in the forbidden positions. And we have now found that R1 is 7, R2 is 15, R3 is 10, R4 is 2, and R5 and R6 are 0. You can't put 5 or 6 rooks in the forbidden positions. And so the number of ways of placing n non-attacking rooks and avoiding the forbidden position, the thing we wanted by the inclusion-exclusion principle, is given by this formula. And now I have all the ingredients. So the final answer for our case, n is 6, and R1 is 7, R2 is 15, and so forth. And so I get this mess, and if I figure out what it is 184. And that's the end of this lecture. If you like this lecture, then like it. If you like to be subjected to videos like this on undergraduate mathematics, then subscribe to my channel. And I will see you in the next lecture.